Hey guys, what's up? My name's Tyagi, and today I'm going to explain to you what atmospheric instability is. The sound of thunder that follows a lightning bolt is unmistakable to anybody who's ever experienced a thunderstorm. The sheer power of a thunderstorm, conveyed through the flash of lightning, the pounding of the rain, and the rumble of thunder, is enough to inspire a feeling of awe in anyone. But where does the energy for such a tremendous force of nature come from? The second law of thermodynamics tells us that energy isn't created or destroyed, it's only transferred throughout a system. So, where is all of this energy coming from? The answer to this question is the same for most things on Earth: the sun. It is our main source of energy on Earth because it provides us a constant stream of low entropy electromagnetic radiation. So, how does this relate to instability and thunderstorms? Check this out. So, this is a diagram of the atmosphere, and incoming solar radiation is coming from the sun, obviously. And only about 50% of this gets past the tropopause into the troposphere, which is the layer of the atmosphere we're interested in because that's where weather happens. So what's happening to the other 50%? Well, about half of this is getting reflected and about half of it is getting absorbed by the upper reaches of the atmosphere, most notably in the thermosphere and the stratosphere. Okay, so what's left of all this radiation that gets to the surface? The majority of it is absorbed by the Earth's surface. And then what happens is that it re-radiates this absorbed heat and energy. And this is why in the troposphere, temperature decreases with height. You may have observed in a plane that the windows frost up, or if it tells you the temperature, like on your TV that they give you in front of the seat, it's like negative 40 degrees outside, even if it's like 80 degrees when you took off. And this is an example of how temperature decreases with height in the troposphere. So it could be pretty hot down at the surface, but up near the tropopause is going to be really, really cold. And this change in temperature is measured by something called the lapse rate, which is telling us how fast temperature is decreasing as we go up in height. So the average rule of thumb that many hikers know for decreasing temperature as you go up in the mountains is 3.5 degrees Fahrenheit per every 1,000 feet. This translates to 6.5 Celsius kilometer, the standard measurement rate of lapse rates. And this is widely accepted as the average of the atmosphere. So now, this is something to think about right here. If the temperature at the bottom of the atmosphere is hotter than temperature at the top, the troposphere, not the atmosphere. At the top of the troposphere, it's colder, right? Then this might be inherently unstable, right? You may have learned that hot air rises and cold air sinks. So wouldn't this hot air want to spontaneously rise and the cold air want to sink, right? This may sound right, but really the atmosphere is much, much more complex than this. In meteorology, a pocket of air with similar characteristics throughout is called a parcel. The parcel theory tells us four main things. The first one is that the amount of moisture within a parcel remains the same as it rises or sinks. The second is that there is no heat exchange between the parcel and its environment. The third is that an unsaturated parcel will rise and cool at a rate of 9.8 Celsius per kilometer until the water vapor within it condenses. Why is this so? 9.8 Celsius per kilometer is derived from the first law of thermodynamics using some mathematical calculations by substituting some constants in and solving equations. The fourth thing is that the moist adiabatic lapse rate is always less than 9.8 Celsius per kilometer. The moist adiabatic lapse rate is the rate at which a parcel that is already condensed cools. So the reason that this is lower than the dry adiabatic lapse rate is because condensation is an exothermic process. It releases heat, causing the rate at which it's going to cool to be slower. The actual rate depends quite a bit on moisture. That's why there is no real constant for this value. So why is condensation and exothermic process? Well, we have our molecules in water vapor. They're all energized. They're moving around everywhere in all directions. They're very, very energized. And they have no bonds with each other. And this is because when it was heated up, it absorbed that heat energy. These molecules absorbed the heat energy used to heat it up, and then in turn they are moving around and bouncing around freely. However, in a liquid, this energy is lower, and there are some weak bonds with them. So it would have to lose some of this energy to its environment. It would lose heat, which in turn would heat up its environment. So that means that the parcel itself can get warmer after condensation without any heat exchange with its environment. And this is actually a really powerful thing. On average, a hurricane generates energy worth of 2,870,000,000 tons of TNT each day just from this process of condensation because of the exothermic nature of condensation. This is nearly 60 times more than the amount generated from the world's most powerful bomb, Tsar Bomba, which was worth about 50 million tons of TNT. So think about that. How much energy is being produced from condensation? So let's look at a theoretical parcel rising from the surface. So here's our parcel. A parcel is always kind of like an idealized situation. It's our best guess of really what's happening to rising air within the atmosphere, because it's a really complex process that is not, to this date, still not very well known, but we can make our best guess with parcel theory. So it rises at and cools at its rate of 9.8 Celsius to kilometer until it reaches 2.5 kilometers. Again, this is a theoretical situation. Let's say at 2.5 kilometers is 45 degrees Celsius, and this condenses into a cloud. So this is going to release some heat because of the condensation, and now the rate at which this cools is going to slow down. So let's say this was 70 degrees down here, right? Let's say it was, just for an assumption, I'm not really going to follow the 9.8 Celsius per kilometer rule. Let's say now it is 60 degrees after that condensation. So it is still unstable because the temperature is higher than that of what it's surrounding. So now it goes even higher. At freezing level, let's say it's still 45 degrees Fahrenheit. And then let's say when we get to 7.5 kilometers, right? Then it reaches the temperature of its surrounding environment, -4 degrees Fahrenheit. And once it reaches the temperature of its surrounding environment, it will stop rising because it has reached stability. It is now the same as the air around it. In this example, I'm just ignoring moisture for simplicity. And let's say if it tried somehow to rise to 10 kilometers, right? Let's say at 10 kilometers, it continues rising and it is -20 degrees Fahrenheit. And the surrounding air, or not -20, let's say that it is -50 degrees Fahrenheit, while the surrounding atmosphere is -40. So what's going to happen here now? It's going to sink. This is called a stable setup because the colder air is on top, not on top, is at the same level of this warm air. So it's going to sink back down to where it is at the same temperature, -4 degrees Fahrenheit, the 77.5 kilometer level. So this is an example of how a parcel could rise from here to here. It's at the 9.8 Celsius per kilometer at the cooling rate. And then from here onwards, it's at the moist adiabatic lapse rate for whatever it would be. Remember, this is just a generalization, but what I want you to take away from this is that a parcel will continue to rise until it is the same temperature and basically the same qualities as its surrounding air, surrounding environment. And if it somehow gets colder than its surrounding environment, then it's going to sink. That's stability. So stability can either be achieved by having the same qualities as the surrounding environment, or by having the air more dense than the surrounding environment. So remember, warm air is less dense than cold air. That's why this warm air is rising, right? But all of this is great. But how does this apply to instability? I'm going to show you that with a great diagram of the atmosphere after this, much better than this one. So as of around 6 p.m. Eastern, this is what the sky looks like right now. You can see there are some bubbly convective cumulus clouds, but mainly they're just reaching a height and pretty much stopping, it seems like. Especially with these gray clouds, they're not really going to produce rain. They just stopped growing. And why is that? Atmospheric instability can be defined as the ability of a parcel of air to rise convectively. So the main method of heat transfer within parcels rising in the atmosphere is convection, because the parcel rises, warm air is rising, and the cool air is coming down. So this method of convection will be explained later in the video in greater depth, but for now, let's look at this diagram right here. So this is called a sounding, a model sounding. So this is the weather model giving us data in a graphical representation throughout the height of the atmosphere at a certain point. So to look at this right now, this is called the Skew-t log P part of the diagram. This is the hodograph, and these are all a bunch of different parameters. So this will be talked about in a later video, but let's focus on the Skew-t log P diagram right now. So this is for 6 p.m. Eastern, for around where I am. Same time I took the video of the clouds outside. And we can see at the surface it's around 86 degrees Fahrenheit. So this red line is the temperature throughout the atmosphere. This green line is the dew point. This blue line is the wet bulb temperature, but we don't really need to know about that for now. And this diagram is actually, it's not really kind of like these lines, the temperature where it says like negative 40, 30, 20, whatever. It's actually not like a straight line. It's actually diagonal. So we can see right here it's negative 10, here's negative 20, here's negative 30. So that's one thing to keep in mind. These lines for where the temperature actually, what temperature is where, is actually diagonal to make it actually easier to read. Otherwise this line would be going, this red line would be going like that. So this is why it's like that. So let's look at this dashed white line right here. So this is actually the parcel path, surface-based parcel path. So we can see we're lifting it from the surface. It's a surface-based parcel. So we lift it, this dashed white line. So it's decreasing at this rate until right here. So this rate right here, that's the dry adiabatic lapse rate. This is cooling at 9.8 Celsius per kilometer. And then right there, that's where it's able to condense based off how the moisture and the temperature are co-located. So that is called the lowest condensation level or lifted condensation level. And that level in the surface-based parcel is 1,901 meters right here, denoted by this green thing right here. And that tells us where the parcel of air will condense and form into a cloud. And then we need to get to a level where the convection will start rising upwards. This parcel will start rising upwards rapidly. That's called the level of free convection, the yellow line over here. And that is around 2,076 meters in this diagram, or for this sounding. And then there's going to be a point where it stops rising because it has the same properties as its surrounding environment. That's called the equilibrium level, which in this sounding, it is 2,936 meters. So right here, that's where the moist adiabatic lapse rate calculations start. You can see it crosses the temperature line right there. So that's where the equilibrium level is going to be and where it's going to stop rising. It's just going to be kind of stuck there. So it won't really be able to develop into anything. That is exactly why outside we were able to see that we were able to see the clouds just there. They weren't really growing into any rain or thunderstorms or anything. So this area right here, from here down to the surface, this area between the dashed white line and the red line is the instability, basically. That's how we calculate instability. So CAPE right here, that's instability in a sounding. Convective available potential energy. It's measured in joules per kilogram. In this sounding, it's 21 joules per kilogram, which is, in the grand scheme of things, nothing. Really, it's nothing. For thunderstorms, you need to have at least 500 as a good rule of thumb, 500 joules per kilogram. 1,000 is preferable, and above 2,000 is considered strong instability, which can be conducive for severe thunderstorms, which will be covered in a future video. And above 5,000 is considered extreme instability. So we can see here, there's actually something that's stopping this parcel of air from being warmer than its surrounding environment, you see how the temperature actually like kind of decreases its rate of, like the lapse rate actually gets lower in this section over here. This is called a temperature inversion. This temperature inversion is causing our clouds to get kind of stuck over there because the temperature of the air around it becomes the same temperature as that parcel. So this is called a cap. This is called capping. This is kind of stopping our clouds and convection from rising any like much higher into the atmosphere. Where the equilibrium level is, that's where they're stopping. So if the surface temperature were to get higher to the point where this parcel would be able to rise convectively to much higher heights in the atmosphere, so like 10, 12 kilometers in the atmosphere around here, then we could get deep convection such as rain and thunderstorms. So if we wanted that to happen with this level of moisture, we would need the temperature to get to 96 degrees Fahrenheit. That's called the convective temperature, as we can see right here. We would need the surface temperature to get to 96 degrees Fahrenheit for a parcel lifted from the surface to actually rise and get into actually any form of deep convection. And that would cause, basically, the surface temperature getting to 96 would cause the lapse rates to become very high towards the surface, which is letting our parcel of air be warmer than its environment, which is letting it rise higher. So CIN is a measure of how much capping there is, convective inhibition. In this sounding, the effects are negligible because like it pretty much doesn't really show too much. But the idea is it's kind of like it's kind of the area behind the red line and the dashed white line. Sometimes say the temperature actually came back behind this dashed white line behind our parcel, then that area where the red line was ahead and between the dashed white line, that would be the CIN. So that capping, in a lot of cases, it can prevent the development of thunderstorms and just like have your puffy white cumulus clouds outside. But in some cases, it can actually fuel development of thunderstorms. Because when, say in like the morning or early afternoon, the environment may be capped. But as surface temperatures heat towards the convective temperature, the capping would be effectively rendered useless because our parcel is starting off warmer and warmer and warmer. And that's going to let it pass that capping without becoming the same temperature. So that can let our actual instability rise in the area between the dashed white line and the red line increase. But again, this will be discussed in a future video. So that now that we know about Skew-t diagrams, let's look at a better example. So this is from Comanche National Grassland, extreme southeastern Colorado. From yesterday, the HRRR models run. There was an enhanced risk of severe weather there yesterday, so I thought this would be a good example because it combines what we just learned about graphs and parcels in a pretty nice way. So this one is for about 12 mountain time, 12 p.m. mountain time. Let's look at our parcel. Our parcel is rising, 9.8 Celsius per kilometer. It condenses the LCL. And look at how our parcel rising is actually behind the temperature line. So that's the cap. And this area right here, where my cursor is, that is CIN. You couldn't really get a good example of it before, but that is the CIN, which is basically 184 joules per kilogram of stability, which is shown in negative. And we can see that this parcel is still graphed because, again, behind it's at this level above this is where it's gonna still be unstable. It's just that this one level right here is stopping anything that's condensing at the lowest condensation level from rising any further to the LFC. All right, so let's go forward in time. This is at 1 p.m. Mountain Time, the cap is still there. 2 p.m. Mountain Time, the cap is still there. 3 p.m. Mountain Time, the cap is still there, but again, the cap is eroding. 4 p.m. Mountain Time, the cap is nearly gone. It's negative 50 now. 5 p.m. Mountain Time, it's barely there. It could still stop, but it's basically gone. 6 p.m. Mountain Time, the cap is virtually gone now. It is -30 joules per kilogram, which is negligible in large scale things. Anything condensing at the lowest condensation level that reaches the level of free convection is gonna explosively erupt towards the equilibrium level, which in this case is at around 12 kilometers, which is generally what it would be in a severe thunderstorm environment. And this is because the lapse rates we can see down here, the lapse rates throughout the level, surface 3 kilometer, 3 to 6 kilometer. This is 850 to 500, 700 to 500 millibars. Just as a side note, millibars are a different measure of height and weather. You would use millibars basically as the pressure within the atmosphere, these pressure and height are not always constant because distance and pressure are not really related to each other. They're used interchangeably generally because their results are about the same, but there's just two units of measuring height and weather. One is pressure, one is height, like in kilometers or meters. So we can see the lapse rates throughout are around 7 or 8 Celsius per kilometer. So basically, remember, after it condenses, the lapse rate of a parcel is going to significantly decrease with that moist adiabatic lapse rate. So there's going to be a lot of time before it really reaches a point where it has similar characteristics as its environment, which in this case is at 12 kilometer. So this large area here, which ends up being 2,400 joules per kilogram, is ample instability for a thunderstorm. So now we know what instability is, but we also know that air does not spontaneously rise to form a thunderstorm, even if the atmosphere is unstable, right? There's got to be some mechanism that causes that air to rise, right? We can see right here that distance between the lowest condensation level and the level of free convection. There's got to be something that gives it that nudge to get to the level of free convection and just rise and become a big thunderstorm. Otherwise, everything would just rise together and we would have a massive mess of storms all competing each other, or just a cloud-filled dark gray sky. Newton's first law of motion tells us that an object at rest will remain at rest unless an outside force acts upon it to make it move. So what is this outside force that's causing air to rise and potentially form into a large-scale convective thunderstorm? This has got to be something that's lifting air upwards and letting it rise freely. So the second law of thermodynamics tells us that energy moves from low to high entropy. In terms of temperature, this means from hot to cold. So the density difference between the warm, less dense air and the cold, more dense air lets the warm air rise, right? But this is not really strong. This is just going to create some pockets of rising and cooling air, which is convection. It is still atmospheric convection, but it is very, very, very weak. So what's going to be stronger than this? Now let's look at something called gravity. So if we have our atmosphere, right, the normal troposphere, we have cold up here, warm, oh, that's the wrong color, but we have warm down at the surface, as we explained previously. So gravity is gonna push the more dense air, the cold air upper, that's over up here higher. Gravity is gonna push this down. Gravity. And then this cold air coming down is going to displace this warm air. It's going to give it a push. It's going to give it a nudge because, again, it's more dense. And the warmer, less dense air now has an excuse to rise. And it's getting pushed by the gravity. The gravity is helping it rise. So now we have a classic convection pattern over here that's set up. So both the gravity and sometimes just the density difference can cause convection in the atmosphere. And in an environment with no capping, this can produce a type of thunderstorm known as air mass thunderstorm. Air mass thunderstorms aren't very strong, but still, we're getting a thunderstorm out of this. So these two previous forms of convection that I talked, one, the density-driven, and the second, the gravitationally driven, are called free convection. However, when mechanical forces are used to generate convection, it is known as forced convection. So let's show an example of forced convection. So forced convection is usually stronger than free convection, and it can be caused by a surface pressure gradient, surface wind friction, large-scale ascent, such as low pressures, dry lines, warm fronts, cold fronts, gravity waves, upper level divergence, lower level convergence, etc., etc., etc. But really, at the end of the day, these are all doing one simple thing. So we have warm air at the surface, cold air aloft, whatever, wrong color, but leave it. Now we have something that's pushing this warm air up. In the example of a cold front, it would be cold air coming in at the surface and then causing this warm air to rise upwards, which then displaces the cold air aloft, and there's our convection cell. So this cold front is acting as a mechanism to but activate the instability that was already there. So this type of lifting is going to help generate stronger convection. So the cold front, just to recap, a cold front is the boundary between warm, moist air, cool, dry air. The cool, dry air is pushing up the warm air, and it reaches the, it's going to just expand. It's going to condense at the LCL, and then because this cold air is pushing it, it'll easily be able to reach the LFC, and then it's just rising. We have our convection cell. And if it never actually reaches a level of free convection, say there's not really any instability for this to activate, then this is going to be called stratiform precipitation. This is really common in the colder months when there's not very much instability in the atmosphere, at least in northern latitudes. And then this is just like the boring kind of rain that's like just rain. It's not really convection. But when it's able to convect, as our example here, then we have dynamic precipitation or convective precipitation. And the rate of precipitation in convective precipitation is almost always higher than stratiform precipitation. And the idea is here that convection is going to have lift and instability. So the lift helps push it up, whether it is forced or it is free, and the instability is going to let it rise and create that convection cell. Later, I'll tell you how a thunderstorm is a great example of this. One last note. Let's talk about virtual temperature, moisture, and parcel levels. There's one thing I left out in the Skew-t and instability discussion, which is virtual temperature. The virtual temperature of a moist air parcel is the temperature at which a theoretical dry air parcel would have a total pressure and density equal to the moist parcel of air. So what this is letting do is actually letting us use the parcel theory in reality by letting us use equations that would usually be used for dry air, for moist air, and vice versa. This lets our parcel be more ideal and helps us show the amount of instability in the atmosphere better. All right, let's look at this in sounding right here. It's the same Comanche National Grassland sounding from yesterday at 12 Mountain Time, 12 p.m. So this red line, solid red line, is temperature, right? But look at this dashed red line right here. That is the virtual temperature. And if you look at where our parcel is being lifted from, it's being lifted from that virtual temperature. So why are we lifting the parcel based off of the virtual temperature? Well, virtual temperature is a function of temperature, moisture, and air pressure in the basic sense. The effects of air pressure aren't really valid in this discussion, but the moisture is really, really important. So just as warm air is less dense than cool air, moist air is less dense than dry air. Why is this? It might not make sense at first, but let's look at the chemistry of air. Dry air is mainly made up of nitrogen and oxygen, and the atomic mass of dry air is roughly 28.97 atomic mass units. However, the atomic mass of water vapor is about 18 atomic mass units. So water vapor is lighter. So the more water vapor an air parcel has, the lighter it is, meaning less dense it is, meaning the higher the chance that it's more buoyant and can rise compared to drier air. So this is why moisture is a key ingredient in thunderstorm formation, and it is a very fundamental concept that can play a large role in how strong convection can get. So if we look at our parcel here, if we were to lift it from the temperature right here, this would be just like straight up first of all, the CIN would be much higher than it actually is. Second of all, the instability altogether will be much lower than it actually is. Let's just forward this to a time where we can actually see thunderstorm formation potentially happening. So look at how the virtual temperature is higher than the temperature at least a solid amount until almost 500 millibars, or around 5 kilometers. So this tells us that virtual temperature helps factor the moisture, and moisture is a really important thing because in reality, we're not having warm air underneath cooler air. We have warm, moist air underneath cool, dry air, which makes it even more unstable because that warm, moist air is even more buoyant compared to cooler air than cool, dry air. So warm, moist air and cool, dry air, that creates the best buoyancy gradient, where the warm moist air can just explode upwards, and we can see that with our parcel path here. The instability is quite high. Finally, there are different parcel levels found from lifting either surface-based right here. So in surface-based, we're using the surface virtual temperature, the dashed line at the surface, and we're using surface pressure to lift it from. We're lifting it from the surface pressure. Basically, in pressure, this term's talking about height in the atmosphere. The second thing is mixed layer right here. So mixed layer, what we're doing in the mixed layer is we're taking an average in the lowest area. It varies with methodology, but basically we're looking at the lower atmosphere and we're averaging the temperature and the dew point. Not the dew point, the moisture, averaging the temperature and the moisture, and then calculating the virtual temperature and lifting the parcel from the surface. Finally, before that we have forecast, which forecast basically calculates the virtual temperature from the highest temperature expected that day. And most unstable takes the area with the highest moisture temperature combination, which is measured through theta E, which is a function of moisture and temperature. And then it calculates the virtual temperature at that level, and it lifts it from that level. So in this example, the most unstable area is something lifted from the surface. That's why the most unstable parcel is from there. But if we have a surface temperature inversion, say this instead of 86, the surface temperature was 50. So we'd have here. Let me show you what it looked like then. 50. Let's say dew point's also 50. Let's mix it. Look at what's going to happen here. The surface-based instability is going to become absolutely. It's not going to be there anymore. So this is obviously an extreme exaggeration, but look at what happens when we lift it from the surface. There's no instability when we lift it from the surface. But if we lift it from the most unstable parcel, which is just above the surface, we still have that instability there. So meaning the storms are going to be more elevated. So this tells us how storms can still form in elevated cases, but we need the forcing there. So to recap, virtual temperature is used because it factors in moisture, and moisture is a key ingredient in thunderstorms because, again, what's coming out of a thunderstorm? Rain. So we want to have moisture and temperature located in a way that it becomes much more buoyant than the atmosphere above it, which lets the parcel rise very high into the atmosphere before it becomes the same as the environment, which maximizes the instability. So we have our parcel rising. As it rises, it cools and expands, forms clouds. Cooling and expanding is called adiabatic cooling. And this rises and rises and rises until it hits the equilibrium level. And a big thunderstorm can form we're not really a thunderstorm yet, but a deep convection cell with clouds, and which could form a thunderstorm, can form when the equilibrium level is high enough and the convection is able to reach high and it is not restricted by anything. So I found this cool time lapse of a thunderstorm on Wikimedia Commons, and this is going to be a great example to show what atmospheric convection is through a thunderstorm. So let's think about this. We have some air coming in from the surface, and it condenses. As our parcel of air rises, it condenses, and then because there's enough instability and we have the forcing, it explodes upwards, and the convection rises and rises and rises until we get to the equilibrium level. So let's look at this animation of the thunderstorm. So we can see parcels rising and condensing, and we can see this bubbling, which is a really great example of convection. We can see how it is almost rising over here and just moving back here. So let's look at this. Look at how it rises over here. The warm, moist air coming from the surface, the warm, moist air parcels coming from the surface that are into an unstable environment, that is called the updraft of the thunderstorm. It feeds the thunderstorm up. So let's look at what's happening here. We can clearly see an updraft is over here, and we can see how the thunderstorm expands within this. Here, let's go back, because right now, actually, this right here, let's look at this. Here, wait for this to go forward, and look at how it's so unstable that this is actually seems to be reaching above the equilibrium level because it's forced so high up. So then it's gonna sink back down, because remember what I told you about it becoming stable in that case. So it will sink back down, as we see later. As we see, all of this comes back down. All of these parcels that are above come back down. But still, that goes to show how instability is quite a volatile thing, and how it fuels these thunderstorms. So this thunderstorm is an example of atmospheric convection. We have our updraft, which is the warm moist air coming in, and the downdraft is going to be located somewhere within the thunderstorm too, which is bringing the cold, denser air back down. So that shows our convection cell pattern. And this is why a thunderstorm is a great example of a convective cell, and how it harnesses instability to create something very, very strong. All in all, atmospheric instability is a measure of how likely it is for a parcel of air to rise due to buoyant forces. Remember, warm, moist air is more buoyant or less dense than cool, dry air. This can lead to convective processes, especially when the instability is on the higher side. The dynamics of a thunderstorm and severe thunderstorms will be discussed in more detail in a future video. Now that you know about one of the main driving forces behind thunderstorms and other forms of atmospheric convection, maybe you'll look at them with a new perspective in the future. Thanks for watching, and I hope you learned something new.